So hi there, everyone. My name is Chandler Carruth. I work for Google. I work on our C++ language platform. I work on our C++ compilers. Specifically, I lead the Clang and LLVM teams at Google. And I'm here to talk to you a little bit about performance and efficiency and making code fast and all the different things that go into that. But before I do too much, I want to actually give you guys a little bit of want to manage some expectations, because I've been reading the Twitter feed from all these folks, and they're talking about all these like crazy good questions. I just want you guys to know this is essentially like my view of what Performance 101 should be, okay? This is going to be kind of an intro talk. If you guys are like hardcore, like really deep performance nuts, you may be a little bit bored, and please be kind, because I'm going to gloss over some things. You could heckle me thoroughly if you really want to. So we're going to talk about efficiency, performance, algorithms, and data structures. And the first thing we're going to do is we're not going to talk about them. We're going to talk about why anyone cares about them. How many folks here think that C++, it's really important to have like high performance in C++? How many folks here think that's super important? Everyone thinks it's important. How many folks here have a really clear idea of why performance is important? Now, all the people who didn't raise your hands the second time, please reconsider raising your hand the first time, okay? We actually need to understand why it is we care about performance in C++ before we just decide it's important. We're going to care a lot about it. So I'm going to tell you why I care about performance in C++. Most of it comes down to a quote from Nicholas Firth, which I will try to pronounce correctly but fail miserably. I actually really like a lot of Firth's stuff. I think he encapsulates a lot of my things that are core to my philosophy about software here. He says software is getting slower more rapidly than hardware becomes faster. Right? This is particularly in contrast to the kind of normal Moore's law approach to hardware's getting faster. Great, all the time. It's okay. We don't need to make software faster, because the hardware will catch up. And it turns out that's not really true. We're really good at writing slow software. Even in C++, we're really, really good at writing slow software. It's hard to write fast software, and it takes a lot of effort. And so it's important to think about why that might matter, no matter how fast the processors get. And to give you an idea of just how much I think that Nicholas Firth is really on the same page, I have to mention, he actually wrote a book entitled Algorithms Plus Data Structures. I did not actually realize this was picking the title of the topic, but Anyways, we're going to come back to this book because he predicted some whole elements of this talk in his book. So, well, how many folks here have read this book? Anyone? All right. Long time ago. It's a good book. It's a good book. Okay. So I actually think that the idea that software is getting slower too quickly, right? It's getting slower at a really astonishing rate is even more relevant today than it has been before. And for pretty specific reasons. There was a very similar event that happened in the technology world some time ago that changed, in my opinion and in a lot of people's opinion, how we look at computing devices, the performance of computing devices, the challenges we face writing software for computing devices. And this event was the iPhone, okay? And when Steve Jobs introduced the iPhone, he was not doing anything particular to C++, but he was changing how we think about computing. Mobile was now a first-class compute citizen. I mean, it took the world a little while to even realize that was what had happened that day. But that's what happened. We now have to care about mobile. We have to care about things that are small, right? Things that are really hard and challenging to fit, big, bulky systems into. And we essentially get into this annoying situation of, we have small, we have fast machines, and we have to choose one. We don't get to choose both. And we're going to choose small almost every time. But it gets worse. Because the other problem that the iPhone introduced that people really weren't as focused on at the time was the problem of a battery. What do we do about the battery in your phone? Your phone's battery, I mean, my phone's battery is about dead, right? How many folks here have charged their phone today? Okay, that's a problem. That's not a feature, that's a bug. Okay? Yes, like how many folks are charging their phone right now? Okay, so we kind of entered this new problem domain. Suddenly, power became relevant. Now, a lot of people talk about there's some kind of shady research out there that I want to push back against. There's some research into power efficient instructions. If you ever read about power efficient instructions or optimizing for power usage, you should become very suspicious. And you should probably run the other direction, because this is mostly total junk science. Okay? Here's the #1 leading theory about how to save this, how to save battery life. Finish running the program. Seriously, race to sleep. That's the actual technical term, is race to sleep. The faster your software runs, the less power it consumes. Now, people get really upset about this. Like, no, if I run software really fast, then it heats up my processor, all that excess heat. That's the wasted power, but it's not, okay? Here's the thing. We've never really figured out how to run processors and do work on processors in a power-efficient way. You know what we figured out how to do with processors that has made our battery lives improve over time? We figured out how to turn them off. This is literally how your phone, your laptop, like if you have a computer on your desk, every single microprocessor, general purpose microprocessor you can get today, the way it conserves power is by turning itself off as rapidly and as frequently as possible for as long a period of time as possible. The more your processor turns on, the less this little green goes yellow and then red and bad stuff, right? So we actually want to make code faster in order to save battery life. Universally, this is true. There are some extreme exceptions to it. There's some really weird stuff out on the fringe, but 99.9999% of the time, you want to run code faster to save battery. Okay. But batteries aren't the only story when it comes to saving power. This is one of Google's data centers, okay? Now, you'll note that this is a very large building, and the only thing it is doing is taking electricity and turning it into heat. That is its job. And it's really good at its job, okay? And unfortunately, electricity costs a lot of money. And in fact, it's a finite resource. There's a certain point at which the cost goes away. You simply cannot have any more electricity at a particular point in time. And so power becomes very, very important in a data center as well. Now, I find it interesting that it's on the two extremes of computing platforms that we find convergence, right? When you drop to a phone, or when you go up to a data center, all of a sudden, power dominates, right? And we talk about compute per watt. This is another picture of the data center. By the way, I just want to clarify what this is because this is one of my favorite pictures. Those are enormous steam vents blowing out water vapor. And apparently, I don't know this, but apparently, when you can see the water vapor, the data center is operating at peak efficiency. Because it means it's not too hot, it's not too cool, it's actually like efficiently cooling this data center. Anyways, random trivia. So we end up wanting compute per watt, and that tends to dominate in the data center. And this is actually kind of the same thing we're trying to pull off on a phone or anything else. We want to maximize how much compute we can get out of the watts we're going to burn while the chip is turned on. Make sense? All right. Now, I say that raw speed isn't everything because when we talk about, performance is really important, you'll get some mixed messages from people. How many folks have heard this adage? After all, Java is faster than C++. How many folks have heard it? Come on, you can be honest. I've heard it. All right, I had James Gosling sit across from a table and tell me I was a complete moron because I didn't believe that Java was faster than C++. And at the time, he was right, and I learned better. So it turns out that Java is faster than C++ in certain very specific scenarios. For example, if you have a specific application, and your specific application is going to run for a long period of time, and you're concerned about the throughput of that application, and you have a very well-tuned virtual machine for your Java, and you've tuned the garbage collector to precisely match the desired kind of garbage collection interrupt frequency for your application. If you get all of that, Java will very often beat the performance of C++. Unfortunately, it's a bit hard, all right? But Java actually can beat the performance of C++. Now, I'm not being entirely serious here. Java's faster, right? Like it will work for all of these things. So why are we here? Why aren't we still using C++? Like why aren't we at JavaCon? I told you I was going to troll some. Well, C++ doesn't give you performance, okay? It's not going to magic up some performance that's going to make your program faster. Java isn't going to give you performance either. The thing that C++ gives you that I think is particularly valuable is that it gives you control over the performance of your application. When you need to fix a performance problem in C++, the means to fix it are fairly direct, available, right? And they tend to not ruin your software, okay? And in Java, this is actually a lot harder, I feel. I think this is why we have this perception of a performance difference between Java and C++. Okay, it has much less to do with the intrinsic speed of the languages and much more to do with how easy it is to take control over your performance, right? To actually change it to work the way you want. Okay, so with that bit of motivation, I want to talk about the two ways that I view performance, okay? My high-level thesis is that there are two kind of sides to the performance coin. One is actually efficiency, not performance, okay? And efficiency comes through algorithms, all right? Primarily, you're going to get efficiency through algorithms. You don't get efficiency through almost anything else. But performance you get through data structures. And I think this is going to be kind of interesting. I don't believe there's a whole lot of performance gain from changing algorithms, whereas you can have tremendous performance gains from changing data structures. Okay? So let's actually dig down and see why I'm making these claims. First thing we need to understand is what I mean by efficiency. All right? Precise definitions here. Well, somewhat precise. How much work is required by a task? Right? You have some task. You want to compute something. How much work do you actually expend to compute that? Okay? Now, improving the efficiency of an algorithm, right? Some kind of algorithmic computation typically involves doing less work. I like this understanding and this definition because it's very simple. You can explain it to people. It's like, well, I could do a lot of work, or I could do less work that gets me the same result, right? That's an algorithmic improvement. That's an efficiency improvement. These are incredibly powerful, right? You almost have to do these, or your software runs terribly slowly, right? And this is what we understand at a fairly intrinsic well, right? Now, a different thing I want to define is an efficient program, right? Not just efficiency, but what does it mean when you are efficient? Well, for purposes of this talk, let's talk about efficient as, when you've kind of reached the minimum amount of work that the particular problem you're trying to solve necessitates, right? For some kind of theoretical algorithmic complexity argument, we believe that this is the best algorithm on the table. We can't do less work and actually get the results we need here, right? That's an efficient program. It does a minimal amount of work. Folks happy with this definition? All right. So, performance, all right? So how do we actually define this? How quickly a program does its work, okay? So the idea here is that if you want to improve performance, you don't do less work. That would be changing how efficient your application is, right? What you do is you actually have to do the same amount of work faster in time, okay? And that's what gives you a performance improvement. Does that make sense to folks? Right? Now, the other thing I want to point out is that there's no such thing as performant. How many folks here think performant is a word?
It is in German.
Performant is not a word. I don't care what Wiktionary or some other user-edited dictionary tells you. Performant is not a word. And there's actually a reason why performant is not a word, okay? There is not a point at which a program is doing the maximal speed of work, right? What is the maximal speed of work? Well, there's actually like this Bremerman's thesis about the limit at which you can compute something, but this thing involves like the speed of light and other like crazy constants. It's just totally unrealistic. There's nothing real about that limit. And so calling something performant as in like, oh no, we're done working on it now, right? It's efficient and it's performant, right? Can't be improved further. This doesn't make sense, okay? And so just erase this term from your vocabulary, okay? Yes? Does it mean, so the question is, does this mean it performs well enough? It performs to a minimally acceptable level. I would suggest saying it performs well enough. As a slightly more precise statement, what is performance? Like the thing is, if you draw the analogy to efficient, right, then it's highly misleading, right? An efficient algorithm we think isn't wasting anything, but like performing well enough could still be leaving a whole lot on the table. I actually would argue that essentially every piece of software that I've ever seen and every piece of software that you have ever seen is horribly slower than it could be, right? So what is good enough? I don't have a good answer here, right? And so I would actually say what you mean there. So what does it even mean to improve performance if we don't have like an end state in mind, right? If there's not this like limit, then it becomes a little bit hard to understand how we're making progress. So I'm going to define kind of a more practical limit here than the like theoretical computational limit according to physics, because that's not useful. Okay. So there are a couple of assumptions that we need to have in order to define what the limit of performance is. Right? The software is going to run on a specific real machine, right? Not some theoretical physical construct. It's not going to store data in a black hole, right? If you read some of the theories about computational, like theoretical possibilities, they actually talk about black holes as computational devices. It's very strange. I don't understand. I'm terrible at physics. I don't understand this. But we're going to run on a specific machine, right? And there is a theoretical limit of the rate at which that machine can process data. right? There's a limit on exactly how quickly it can do any particular task we give it. There is an actual theoretical limit to that. And that's a limit we should be striving for. Another way to think about this, which isn't an entirely accurate, but I find it a very useful way to think about this, is that we were trying to light up all of the transistors, right? We're trying to actually engage the entire chip, the entire piece of hardware available to do a computation in order to do that computation as rapidly and effectively as possible, right? All of these things, we want all of them rather than, because usually we get like a little tiny piece down here to work on our problem, a little tiny piece up here. Folks know what this is? Okay, this is the Sandy Bridge Intel CPU, okay? Sandy Bridge Intel CPU. There are 8 cores on this thing. There's a bunch of logic processing down here, or no, this will be the cache and logic processing up there, one of them, right? You got more cache in this middle section, and you've got a bunch of cores. These little mirrored sections on each side, those are the cores of the CPU, okay? And you can kind of see the layout. It's very similar. There's a lot of symmetry to it. But the really fun thing, and I couldn't find an image of this, is they've done some heat maps of the CPU when you're doing computations to see how much of the chip you're using to do work. And it's very little, right? It's actually very, very little. And so that's actually part of the problem, okay? It really all comes back to what? If we have circuits, if we have traces on this chip that we're not using, then we are wasting them. I mean, the chips do amazing things to mitigate this. They'll actually turn off whole sections of the chip to save power, like subsections of the core we turned off to save power. But ultimately, we're still wasting at least the space to actually put those pieces of the chip in. Right? We could have a faster chip if we just made it all the parts that we were going to use, and if we could use all of them. Now, don't take this to the absurd level, please. I've had a bunch of people who've heard this argument about lighting up all the transistors, and they're like, well, I could light up all the transistors, buddy. Like, just give me 1 minute here, I'll light up all those transistors. And I'm not talking about that, okay? I'm really talking about using productively the entire chip, right? Trying to effectively leverage the hardware that we have. Make sense, folks? This is how I think about performance. Okay, so let's talk about how we actually get better efficiency through algorithms. All right, algorithms, I think you guys probably have a pretty good understanding. How many folks here have had an algorithms like complexity theory class? Everybody's hand goes up, I hope. Okay, I'm not going to spend lots of time on this, right? These algorithms are really nice to work with, right? You can play with them in higher level languages. You can experiment with algorithms. You can figure out how they're doing the work, where they're wasting effort, right? It's really, really easy because it carries across all the languages. It doesn't matter what your processor is or your system looks like. Algorithmic complexity is this like really nice common mathematical concept. And so I'm hoping that you guys are good here. You're really good here. But don't get lazy. You have to pay attention to your algorithms. It's incredibly important. It's more important than everything else I'm going to say. The only reason I don't spend more time is that I think you guys have a very good understanding of this already. So the only thing I want to actually spend some time on is a particular example of how you need to adapt your thinking when you're actually writing software to see that there's an algorithmic opportunity. Right? I know you guys know how to analyze algorithms. I know you guys understand what the complexity cost is. But how do you break out of the model of writing software to think about like, oh, hold on, there's a more efficient algorithm here, right? And it all centers around doing less work. You have to realize when you're doing work that you did not need to do. And my example here, my favorite example for algorithmic improvements is substring searching, because everyone knows about substring searching. It's old, right? It's been well done. Marshall over here has been through this about 80 million times. Hopefully I haven't gotten any of this wrong, Marshall. Like heckle as much as you need to, right? So of course you start off doing substring searching and you get an n-squared algorithm. You folks probably understand why this would happen, right? You're looping over the string looking for your substring, right? But you're also looping over your substring to see if you found a match. And that means you can actually loop, twice over everything. It's no good. Well, there's some kind of obvious waste here, right? You're looping over the substring many times, right? That's work, right? Is there a way to not do that work? Right? And the first approach we have, right, is kind of the Knuth-Morris-Pratt approach, which essentially loops over your substring, computes some special table information so that you can actually skip ahead as you're scanning for a match, right? So that you don't keep iterating over your substring when you're looking in the larger string, right? That's how you save work. It's an algorithmic improvement, right? And the second one is Boyer-Moore. And this one's kind of really interesting because it realized, well, you still spend all this time at the front of your string. Right? We can do way better than that if we jump to the back of the string, because we'll skip over whole chunks of the text we're actually searching in, not just skipping over the substring, right? So if we can start at the back, then however long our needle is, that lets us jump ahead faster. We do less work. You want to look for ways you can do less work anytime you're dealing with an algorithm. Makes some sense? Excellent, excellent. Okay. There's yet another perspective on doing less work, though, that has nothing to do with algorithms. Okay, and I want to talk about this because I see this come up time and time again, where people don't understand why their code gets kind of slower and slower and slower over time, and they profile their code, and nothing in their code is slow, just kind of everything's kind of not fast. And they'll come to me and they'll be like, well, what did I do wrong? And usually I'll spend 5 minutes looking at their code, and I'll find 100 things that they did wrong, and none of them will make a difference. Okay? This is very frustrating. Now, a lot of this, not all of it, sadly, sometimes the problems are much more subtle, but a lot of this comes from kind of systemic, minor efficiency problems that don't have to do with algorithms, they just have to do with mistakes. And they're easy to make, so I want to call them out so you guys really, really watch for them. These can cost you a tremendous amount of performance. Okay, so here is a very basic code. Does anyone here think that this code is slow? Got some hands, okay. So you'll probably know exactly what I'm going to suggest doing. I'm going to suggest that we don't actually need to allocate memory every time we do pushback. We can reserve it ahead of time. We know how many elements are coming in. We can jump right to the end and just have the memory available. Right? Now we've added a line of code. How many folks think that this code is more complex? How many folks think this code is more complex? A little bit more complex. Right? How many folks think that this code is more clear? I actually think this code is a lot more clear, because now I know that you actually expect this pattern. This wasn't a mistake, right? You didn't do something by accident. There was no accidental goof here with your pushback. You actually meant to push exactly as many elements as were in this input, right? It makes the code very, very explicit. I like that, okay? The nice thing is it also removes wasted effort. We do not need an amortized growth construct to do this efficiently. We don't need all of the complexity that vector brings along for the ride when we don't reserve. All right, so by taking a very simple step of explicitly documenting what we want to happen, we actually make the code more efficient. Okay, make sense? All right. What about this code? How many folks think this code is reasonably efficient? No one, good. Okay, how many folks think this code is big O 1? Anyone think this code is linear? I'll give you a hint. This code is linear. Okay, so what's going on here? We have a string key, right? We have a giant map of data structure, right? We look up a key in the data structure. This is a silly, silly memoization example. It's a very silly example, but it comes up a lot in code. Now, who here thinks this code is linear? Linear in the length of the key. The code is linear in the length of the key. Okay, let's assume our key is small. How many here think that this code is linear? Stefan?
It's linear because if that key is controlled by an attacker, of course it has to go.
Yes, okay, so Stefan points out a very subtle thing that if you have some malicious attacker attacking your code, they can actually force the key to always go into, anyways. I'm not worried about malicious. Why is this just boringly bad? Okay, it keeps computing the hash of this key. So every time, so the way unordered map works, all right, we give it a key, it has to compute a hash, it takes that hash, it has to fit that hash into a hash table, it looks up in that hash table, it then chases some pointers, then finds some data, and it gives you an answer. Now, how many times do we do that here? We did that like 4 times, okay? And we got the exact same result every single time. Okay? We do not need to do this 4 times. This is actually really expensive. I have found a preposterous amount of code which is actually slow purely because of this pattern. Okay? I'll get to why it's slow purely because of this pattern. But the key to realize is that you're wasting effort. All right? We can do this much more efficiently. Not increasing the performance. We can just do less work. All right? We add this one simple variable, and all of a sudden this code becomes fast. Okay? Very, very straightforward. Now, why do I bring up these simple examples? I bring up the simple examples because it is critical that you always do these things. okay? Not some of the time, not after a profile discovers a problem. You won't find a profile that points to these problems. That's part of what makes them really tricky, okay? The key here is that you always want to do these things because they don't actually make your code worse. If your code isn't important to performance, fine, okay, it's still readable, all right? It's not getting a lot more complex. You're not adding a burden for a future maintainer, right? If anything, you're making it more explicit and clear what the intent of the software is, okay? You should do these things by rote, by habit. You should do them everywhere in your code, right? This is one of the things that I learned working on the LVM and Clang open source projects because they are absolute zealots about this stuff. They are crazy about micro-optimizing these kinds of things. And people get angry because they're like, but this is a micro-optimization. And it's really not. Like, sometimes they go overboard and they ask you to make your code more complex or less readable in order to achieve something like this. But this is not more complex or less readable. Like, anyone here think this is more complex? Anyone? Because I actually think this is way less complex because I actually pulled out one thing. There's nothing else going on here. This isn't a micro-optimization. This is just writing elegant code that happens to also be very efficient, okay? And this is why efficiency is so much more important than performance, right? You can make small mistakes like this that they can add up in cost. Yes? So the comment is that, in this case, I'm also using the default constructor on the object in the dictionary. And yes, I am. However, there is no way with unordered maps current interface to insert something without that constructor. So the question is there a balance between the default constructor and doing it this way? And not really. So I don't think this is too bad because if you look at the old code, right? I was going to default construct this anyways. All right, no matter what I do, I will default construct it first and then insert into it. There are other ways to check. I actually don't think that those matter a lot, and they're much harder to read. And my whole point is that you shouldn't do something that makes your code hard to read for the sake of this. But you should do it when it's actually not hurting your code at all. And one of my questions about actually the standard library is I actually think it's a real problem that it makes your code more hard to read. The other problem is, and this is, I wish I had put this on a slide. So if you do, so the idea here is that you can do a find, and you can use find to determine, oh, this isn't in the unordered map without ever constructing the object, right? And then you can only insert into it if it isn't. However, that actually will compute the hash twice. That will actually do the lookup into the hash table twice. And that's almost certainly more expensive. If that isn't more expensive, it's expensive enough to remove. Make your default constructor cheaper, or don't store really huge objects in hash tables, right? There are other things to store them in. Make sense? And you'll note that I used an example here of a unique pointer in a hash table. I actually think this is a great design pattern, or at least it could be a great design pattern, which keeps your lookup table very small, very efficient, and keeps large data kept to the side. Yes, question?
I happen to agree with you that we should do this. But on the question of whether it's more or less complex, I'll give sort of a devil advocate argument, which I think is the code itself, I think, is not more complex, but it does require more concepts to understand for a new developer who needs to be less familiar with things like references or memory allocation and reserving in your earlier example.
Okay, so the comment is that this may actually be more complex in some senses, because while the code isn't getting more complex, there are some more C++ concepts at play in this code, which a reader would have to be aware of. I can't really disagree with that. However, I don't believe that it is possible for a programmer to effectively and correctly use a C++ data structure without understanding references and how they interact with that data structure. And so I'm not particularly worried about adding that burden. I mean, I'm a little worried, but not a lot worried. Yes?
I would argue the solution to that is code review.
And there's a comment that the solution to that is code review. Another question? So the comment is, would it be better to insert, which returns a pair of Boolean iterator, rather than to just directly grab a reference? That's actually a great question. If the default constructor were not really convenient for determining whether or not it's in the cache, I would agree with you. But if you imagine writing out the code with the insert, it will be horrible compared to this code. Okay? Now what you may be pointing out is just how bad the interface to this data structure really is. I'm going to come back to that. Okay, so there's a whole other part of the talk about that. Okay. So always do less work. Always do less work. One more question.
Just a statement, don't call reserve in a loop.
A statement, don't call reserve in a loop. I don't believe I did.
You did not.
Okay. Yes, I agree. Don't call reserve in a loop. Call reserve when at one point you have a priori knowledge. This is the likely or desired size. Yes?
Previous example, didn't you return it by value?
I did return by value, yes. So the comment is, didn't I return this by value? I did, and I should not have because this is subtle, and I apologize for being subtle in a slide that's supposed to be interesting. This is more efficient than moving it, but that's a bug in the language. So most unfortunately, if I were to move this local variable into the result, that move construction could not be elided by the compiler. However, because this happens to be the first variable that I declare, and because I return it from the only return statement, I can actually have named return value optimization fire here, completely elide the copy, and it's more efficient. Again, I am sorry, I did not mean to dive into that level of detail. We're not supposed to be focused on the return value here.
You can also pass, the pointer to
So the comment is that you could pass a pointer into this. I please don't. That's bad. Okay, so why is that bad though? You could pass a pointer in, but when you do, all of a sudden, there's no way to tell where that pointer came from. There's no way to tell whether that pointer points to, the same thing that stuff going into X's constructor points to. We lose a ton of information about what the semantics of this program are. And if you actually have a very nice optimizing compiler, it loses that information as well. And you'll see it actually produce more poor code. Output parameters are not faster. It's kind of a myth. Okay, return value optimization, named return value optimization, and move semantics essentially remove the need for output parameters from a performance stance. There are extreme edge cases where they still matter, but they're rather extreme. And they usually aren't strict output parameters. They're usually input-output parameters, which is just a totally different beast. Okay, so trying to make a little bit more progress. So always do less work. The other thing I want to mention is I don't just want you to be thinking about this with the STL data structures. Those are important, right? But you guys are going to be designing your own APIs. And when you do, you need to be thinking about allowing the users of your API to do less work when they know they don't need to do the work, right? This is actually a two-way street. Both the design of the API and the usage of the API have to work in concert to actually have efficient code here. All right. So let's talk about performance and data structures. All right. So I'm going to give the game away. Discontiguous data structures are the root of all performance evil. This is simply a fact. If you don't believe me, I will try to convince you. Specifically, please say no to linked lists. Okay? Please say no to linked lists. There is almost nothing more harmful you can do to the performance of an actual modern microprocessor than to use a linked list data structure. So why do I say that? First, we need to understand the context here. Have a modern processor, right? All of my numbers, by the way, are targeting an Intel Sandy Bridge CPU, x86. I'm sorry, I don't work on ARM. If you work on mobile devices, this will be a little bit less relevant, but not much. So we have, roughly 1 billion cycles per second, which is kind of an annoyingly big number. We have 12 cores in every, socket on your motherboard, right? We have 3 execution ports per core. This is essentially how many instructions that core can execute simultaneously, because your chips are actually executing multiple instructions in every cycle. This means that we can execute something in the ballpark of 36 billion instructions every second. Okay? Now, unfortunately, most of that time is spent waiting for data. About 50% of that time in almost every application. In some applications, upwards of 75% of that time is actually spent waiting for data rather than executing instructions. If this horrifies you, good. It should, right? This is terrible. Right? If you ever wanted to know why software is getting slower so quickly, it's because of this. We need faster memory. Unfortunately, we don't know how to build faster memory. Right? We would like to build faster memory, but we have no idea how to. So what do we do? At this point, you need to understand how the memory architecture and hierarchy of a processor works. And the best way to understand this is with, I think, literally my favorite table of data about performance in the world. Okay? So this is from Jeff Dean works at Google. You may have heard of him. He's kind of smart. He knows a lot about performance. He wrote this down because he kept getting questions and he kept getting into discussions, which pivoted, the disagreements in the discussions pivoted around a different understanding of kind of the basic back-of-the-envelope timings of different operations. And so he just summarized how they break down. Okay, so the ones we really want to pay attention to here are these ones with L in them. L1, L2, and down here we have L3. Oh, he doesn't have L3 in there. And main memory, right? So main memory is way down here, okay? So the way modern CPUs work is they have layers of caches on top of main memory that are much, much faster. But the trade-off they make for being much faster is that they're very small, right? They can only hold a very small amount of data. And the way they hold small amounts of data is that you have a line of data, right? Some number of bytes of data. It's usually very small, around 64 bytes, 128 bytes, something in that range, right? And this line of contiguous data is held in the cache. And it can hold some number of these lines of data. Maybe it's 100,000, but it's not millions and millions and millions of them, okay? And so you run out, right? The way the processor fetches your data is it asks the L1 cache, because that's the fastest one. Do you have that data? And it's really fast. But the L1 cache is tiny, all right? And if it doesn't have the data, then you fall back to L2. And if that doesn't have the data, you fall back to main memory. And we're at 20 times the speed of L2. We're at 200 times the latency of L1, all right? So it's roughly 100 times slower than a cycle. Now, when you think about, you have one cycle. We can execute, right, some 36 operations in a single cycle. And it takes 100 cycles to get a byte of memory into the processor. We have a problem, okay? And the only way to solve this is actually to get your data into one of these higher caches that's actually going to be faster. There is no other solution. You have to get your data to fit, okay? And so everything is designed around having contiguous data and a small amount of contiguous data so that it can stay reasonably populated in these L1 and L2 caches. Modern processors also have an L3 cache that's even larger. It doesn't really matter for the explanation, though, right? It's caches all the way down. Caches all the way down. Okay, so how do mainstream data structures then interact poorly with this? Let's look at standard list. Anyone here use standard list in code? Come on, some of you have used standard list. No, it's okay, don't be embarrassed. Some of you use standard list. I've used standard list in code, okay? Now, it's a doubly linked list. It's very nice. It's very generic. It's very flexible. It's got a great API, well, an okay API at least. Each node is separately allocated. That's actually its killer. Each node is separately allocated. That means that those nodes could be placed anywhere in memory they like. There's no predicting, okay? And every traversal operation on a list has to chase pointer after pointer after pointer, pointer from node 1 to node 2 to node 3 to node 4, right? You guys know how linked list works, right? Okay, right? And that's really slow. Essentially, every single time you traverse that pointer, you take a cache miss, right? You drop down this hierarchy, right? And so every time you move from one node to the other, assume that you have essentially a 1% chance of being an L1, maybe a 10% chance of being an L2, and a, more like an 80% to 90% chance of being in main memory, and you'll understand why these things can be incredibly slow, okay? Now, if you're lucky, right? If you're lucky, or if you work very hard, you may be able to pack these things slightly more densely, but you're not going to get lucky for long. You're going to actually have cache misses, okay? So standard list has a real problem there. Now, it does have a good use case. If you very rarely traverse your data structure, I mean very rarely, right? Algorithmically rarely, it can be very useful for improving the algorithmic properties of updating your data structure, right? And that's where a linked list really shines. If you traverse your data structure, on the same order of magnitude number of times as you update your data structure, you should never use linked lists, ever, right? It's just terrible. Making sense to folks? Anyone want to challenge this, or are you all just you're drinking the Kool-Aid, you're happy? I mean, I'm good if you guys want to drink the Kool-Aid, right? That's okay. So just use std vector. That's what it all comes down to. Just use a vector. It's better, okay? Now, a lot of people respond but what about stacks or queues? Well, okay, a vector is a stack. Yes?
So what about iterator validation?
The question is, what about iterator invalidation? The answer I have to that is yes, some problems are hard. Still don't use the linked list. In a more serious answer to that question, there are good ways to avoid iterator invalidation. And I'll actually mention one because I'm going to hit an issue of iterator invalidation. OK, so vectors are stacks, right? So you're done. But queues are actually interesting. But there's this great trick you can use to make your vector into a queue most of the time. If you have an unbounded queue that just grows like for the entire life of your program and is totally huge, this doesn't work so well. But if you have a reasonable bound on your queue, either on the lifetime of the queue, or you know roughly like the maximum number of elements you'll ever want to insert into the queue, you can use a much nicer approach. Have a vector, insert the things into the back, and just don't remove them from the front. Keep an index, right, which you move forward through the vector, and because you're not removing them from the front, you won't invalidate anything, right? You're not going to invalidate the indexes into this vector. It's very, very convenient that way. Don't keep actual iterators because pushing onto the back of a vector will invalidate iterators. All right? Indexes into vectors are actually really, really powerful because they are invalidated less often. All right? And then just keep your index moving forward. You can even move out of the front object, right? You can just leave the little like husks of partially formed objects if you like Sean Parent's view of it, or default constructed objects if you like Eric Niebler's view of things, right? Whichever one you want, like you can actually get all of the efficiency you really need here, as long as you're okay essentially having a vector the size of the total number of elements you need to process. Now, you can't always do that, but when you can, it's a much more efficient data structure. And there are kind of variations on it where you can essentially reuse a vector in various ways to achieve much the same results. It's a little bit like a garbage collected queue. Yes?
Wouldn't a deck be easier?
The question is, wouldn't a deck be easier? If the standard had a good deck, it would. Unfortunately, the standard deck is one of the worst data structures I've seen. The particular requirements on the API mean that implementing deck is just horrible. And for some reason, every single standard library implementation I've worked with for the last 8 years has been even worse than the interface mandated. So I avoid it like a plague. I'm much more likely just to re-roll what I need on top of a vector. The other reason that I tend to do this is because you rarely need all of the power of a deck, right? The deck is kind of the Swiss Army knife of segmented, almost amortized, but somewhat linked data structure. And usually you need like 1 or 2 of those features, not all of them. And when you only use 1 or 2, the performance tends to be tremendously better. Now, I would encourage you to not do any of this until you've profiled, because we're not in the efficiency bucket anymore. We're back into the performance bucket. And this, I admit this is complex, but I think it pays off in the performance. Now, maps are kind of tricky. Maps are kind of tricky, because you can't just easily like rig up an associative data structure out of a vector. It takes a little bit more work. There are ways you can do it, but it takes a lot more work. Unfortunately, using standard map is an exercise in slowing down code. Okay, if you think that a linked list is bad, maps are worse. I'm going to be really blunt here. I have no code that I have ever worked with which should have used standard map. I don't believe there are problems in real software that it solves effectively. Okay, so maybe a somewhat radical position, but I would actually just strike this data structure from the library if I could. Okay, why do I think that? That seems radical and crazy. So here's the thing. Standard map, it is a linked list. But it's a linked list where all of the non-traversing operations are essentially removed. Okay? Because if you want to insert into it, you have to traverse it. If you want to remove from it, you have to traverse it. Even if you play all of the tricks, you pull out the insertion hint element into your map so that you immediately jump to the right node of your binary search tree to insert, a decent chunk of the time you're going to rebalance the tree, which is a terrible traversal, okay? And one of the slowest things you can do on a cache-oriented architecture, okay? Standard map is terrible. If you absolutely must have a sorted associative container of things, then what you really want is just a sorted sequence of things and binary search your way to associativity on top of it, i.e., just use a vector. Don't use map. But wait, unordered map will save us, right? Unfortunately, unordered map will not save us. Standard unordered map is to me much more frustrating. I despise standard map because I don't feel it's a good tool for any job. Right? It's a bad tool for a rare job. But standard unordered map is more frustrating to me because this is actually the job you usually have. You usually just want to associate a key to a value. And an unordered map, despite the somewhat cumbersome name, seems to do exactly that. But it does so in a terrible way. Okay? So it is essentially required, based on the standard, to be implemented in terms of buckets of key value pairs. And I can't express to you how much of this implementation detail bled into the interface. you can actually get bucket iterators into an unordered map. How many folks knew this? You can get a bucket iterator into an unordered map and iterate the elements of a bucket and observe where they start and where they end, right? You can also get an iterator over the buckets in the map rather than over the elements. It's incredibly hard to build a map which does not actually use separate buckets from the hash table as a consequence, all right? And so what you end up with is this great hash table, which has a pair of a hash value and a pointer in it. Sorry, usually just a pointer in it, right? And this pointer points to, oh yeah, a linked list of the key value pairs that are in the map. So we're back to linked lists. Despite the fact that we were going for the efficient data structure, these hash tables and all the other great things, at the bottom it's actually a bunch of linked lists. All right, they're back. So the performance of this is actually pretty terrible. You will always have a cache miss when looking up into an unordered map. I mean, the first time. You might get away without having a cache miss the second time, but the first time you're essentially going to take a cache miss because you're going to be chasing too many pointers. It's extremely frustrating, okay? And the other thing that's a little bit frustrating is it's not that we don't know how to do this better, okay? A good hash table looks something like this. You don't use buckets. You use open addressing into a table of key value pairs. Right? Just a flat, contiguous table of key value pairs. You use local probing to find where to place values when you have a collision. The local probing here is key, okay? You will have collisions in any hash table implementation. You're going to have them. You have to plan for it, okay? By finding an adjacent or a quadratically adjacent node to insert your key value pair into, you actually maximize the cache locality of handling a collision. The difference between doing something like what I describe here, an unordered map, is massive. We're talking orders of like 10x performance reduction sometimes when this is in your critical path, when you have a high load factor on your hash table. It's really, really bad how this actually performs in the real world. So it would be very nice if we could do this. The other thing I do want to mention is if you design your hash tables this way, you then have a constraint, which is a little annoying. You have to keep your key in values small. So if you have enormous values, right, suddenly they're a little bit more awkward to deal with. But there's an easy solution to that. When you actually have an enormous value, like a really big chunk of data, that's when chasing a pointer starts to make sense, right? And so you can put your value as a unique pointer to the actual large data. You keep a very data-dense, very efficient table structure despite having a large chunk of data. Okay. So if I can get my next slide. That's my idea of efficiency through algorithms and performance through data structures at a very high level, right? Like 101, okay? I would love to stay up here and talk to you guys about the details here for another like 2 hours, but I think we'll probably get hungry. So the only thing else I want to mention is that this is all a lie. So unfortunately, it's not quite this simple. I am sorry that it's not quite this simple, but things get a little bit more complex. You can't just pick your algorithms in isolation to achieve the efficiency constraints you have, and then when you profile, go over and pick your data structures based on those things. It doesn't work that way, right? Data structures and algorithms are actually intertwined, right? And this is actually what Nicholas Verth's book was all about, that these two things, one informs the other. And most importantly, data structures have this tendency to inform your algorithms. And so you actually have to think of both of these at the same time. You can't manipulate them in isolation. You have to understand why you're considering a data structure change, right? That's driving your performance considerations. And you have to understand why you're considering an algorithm change. That's driving your efficiency considerations. But you're going to potentially have to change both in concert in order to actually have them work together, okay? Now, the other thing that's really frustrating is there are some places where what I described just isn't true. Okay, not all performance is rooted at data structure failures. Sometimes you have an algorithm which actually just imposes a data access pattern on top of a perfectly nice data structure that ruins its performance on modern processors. And so don't ignore the possibility of kind of a reversal of the roles here. It's very rare. I would encourage you to start off thinking about things in terms of algorithms for efficiency and data structures for performance, but it's by no means a hard and fast rule. The final thing I have to mention, just for full disclosure, we also are subject to some worse is better problems in the real world. There are going to be cases where the exact opposite of everything you know or want to believe will be true. For example, bubble sort is the fastest sort algorithm for small data sets. Despite being quadratic and like algorithmically and being a terrible idea most of the time, if you have under 64 like elements and they're all numbers, bubble sort will probably win over anything else. It's really frustrating, right? Worse is better. And the reverse kind of property is also true. So there was this great paper about cuckoo hashing, or cuckoo hash. Anyone hear of this crazy idea? It's insane. Okay, so I'm gonna explain it in like 5 seconds. And the idea is you know how a hash table works, right? You have a hash function of your key, right? You modulus it by the size of your table. You look up that slot. That's where you put your entry, right? But what happens when you have a collision, right? I'm suggesting you use very localized probing right around the colliding spot. Well, there's another way you could do it. Cuckoo hashing says, no. Just rehash things. So there's a backup hash algorithm that you can use. And so if you hit a collision, you swap out with the guy in the spot, and you use the backup algorithm on that entry's key. And you find a different entry for it, and you put it there. And if you have a collision there, you do the same thing again, right? And you keep going, right? And it turns out that there are all these beautiful properties of this. It fixes all of the complexity bounds of hash tables. Everything becomes amortized constant time. The hash table is beautiful and self-balancing in the collision space. It's glorious. Unfortunately, it means that you have a locality hostile probing pattern. So every single probe is a cache miss. Essentially guaranteed, because you're guaranteeing it's rare too. And so it's never going to be warm in the cache. You're always going to take a cache miss, and it's actually significantly slower in practice than localized probing, despite having better algorithmic guarantees across the board. It's really, really frustrating. Okay, so with that, my takeaways are, number one, efficiency and performance do matter, and they matter today more than ever. Batteries, small devices, these things really, really influence it. C++ doesn't give you performance. It helps you control it. It helps you make your performance better, okay? Please do be mindful of your algorithms, right? You want to develop pervasive habits of using APIs in a way that avoids wasted work and designing your APIs to facilitate that use, right? You want to use contiguous, dense data structures that maximize cache locality. And I hope that you have some fun writing some really fast C++ code without making your code reviewers cry in the end. And I hope that this is all true and you guys have enjoyed this, whether your performance concerns look something like this or more like this. Otherwise, questions? Questions? By the way, before you ask, we do have microphones up, so if you want to stand up and go up to the microphone, then we will all, as Scott reminded us, hear your dulcet tones.
So can we have vector with in-place storage for small sizes in standard?
The question is, can we have vector with in-place storage for small sizes in the standard? What do you mean by can? So unfortunately, in C++ 98, so fun factoid, in C++ 98, it was actually a conforming implementation to embed a small buffer of memory inside of your standard vector implementation. And as long as the number of elements was below the size of that buffer, you could store them in line. And this is great. You don't have to call an allocation function. It's essentially perfectly cache local, really, really efficient. Unfortunately, this fact essentially no one seemed to be really aware of it, and it was broken in C++ 11 by a very subtle change. In C++ 11, we added a move constructor to standard vector. And the move constructor for standard vector has this infuriating requirement. It does not invalidate any iterators on move. This is the only barrier to having a small size optimized vector, but as far as I can tell, it's a deal breaker. And Stefan, I know you want to say that it isn't, but it is.
It's swap. 98 swap said it does not invalidate iterators, and that was the barrier. And move traditionally. So it never was possible even in 98.
Anyways, this is silly, and we should fix it, but I don't think we can break existing code. I actually regret this. I think this is a terrible mistake. I believe that so the small size optimization is so valuable that we went out of our way to to force it back into standard string, right? But we have no attempt to do this with vector. It's tragic. All right.
So, do you have a Google Code version of a map that has all of these cool features?
Do I have a Google Code version of a map that has all the cool features? So there is one. The open source project is really annoying to find and use. It's like, I don't remember what it's called, Goog Perf Tools or something. It's in this really weird repository. It's called Dense Hash Map. You can find it. It's been copied into Chrome, and it's been copied into a bunch of other open source projects. Protocol Buffers has it. The problem is, and I'll forewarn you, our implementation is suboptimal. No, suboptimal is the wrong word. It's actually really, really fast. It's just really, really ugly. Okay, so the API design was not great here. There are a lot of warts in the interface. I don't really recommend it wholeheartedly, but if you need the performance, yes, go and find it. If you actually search for dense hash map with underscores, you'll probably find it. Other questions?
Hello. What about a custom allocator for a map?
So what about a custom allocator for a map? So you can do that. And I'm sure that John Lakos has been thinking that the entire time I've been standing up here talking. Unfortunately, I have two problems with that. One is that I have maps which are on interface boundaries. And those interface boundaries are ABI boundaries, and so they're not templates. And that makes adding an allocator to a map really hard. Okay? So the fact that allocators are in the type system essentially means that for a large number of applications, it's unavailable. Now, even if it is available, the other problem is that while map gives you a little bit of locality, it's pretty common that your map types are actually about the same size as your pointer types. And so you're getting essentially half the locality that you could have if you didn't have those like left and right hand side pointers in there. And so it still ends up losing compared to like a dense hash table. Other questions? Going once.
I'll make one comment. We use pooling for our node-based containers, and that actually has a fairly substantial effect.
John says that they use pooling and it has a substantial effect. I don't disagree. It totally makes it better to use an allocator, right? The problems I have is that it's of limited applicability, unfortunately, because of the type system stuff. And I know you guys are working on fixing that.
Pool, not allocator, actually built into the data structure is an adaptive pool.
Okay, so you're saying that there's a pool built into the data structure.
Yes.
Okay.
It makes a huge difference.
If I had a standard map with that, maybe I would like standard map a little bit more. I suspect that the left and right hand pointers would still make me grumpy though.
Check the open source distributions.
Okay. Another question.
Okay, so now that we're all going to use standard vector
Yes.
instead of anything else, right?
Yes.
Have you guys looked at the latest Facebook vector optimization? And is it relevant?
Yeah. Oh, sorry. I promise that was not the question. I'm not allergic to Facebook, I promise. So I've looked at it some. I have some problems with it. To be fair, I haven't looked at maybe the latest one. So back when they released their original string and vector optimizations, I looked at it pretty carefully. And unfortunately, it does a lot of semantic changes to achieve one particular benefit, right? And the particular benefit is essentially the ability of the operating system to do a reallocation, right? To just reassign your pointers in the page tables and give you more space without moving data around. And that works really, really well if one thing is true, and that is that your address is not part of your identity. But there are a very large number of objects in real-world C++ code whose addresses are part of their identity, and it's a really subtle thing to teach programmers about. That, why did your performance slow down by like a huge amount? Well, because your address entered into your identity, and so we turned off all of our data structure optimizations, right? It creates this bimodal world where this seemingly unrelated, like minor change to your implementation triggers a cascading deterioration of performance of data structures. And I really don't like that. I would like to find better ways to do it. And the other thing is that the performance benefits of that don't seem to be all that significant. I think a lot of the other performance benefits they got were just from tuning the vector implementation, which it's in pretty sore need of. I mean, it's kind of, a lot of the standard library vector implementations are much neglected because it's just a vector. Why could it possibly matter? For example, I think that the growth factor for a lot of standard library vector implementations has like been historically wrong, and it's only recently they've gotten made more appropriate.
What growth factor would you like?
So the question is, what growth factor would I like? And I would not like say that off the cuff. I would have to go back and dig up the people who did the work to demonstrate what the correct growth factor was. It was a very small difference that preserved the algorithmic properties, but turned out to be much more efficient. It wasn't like 12. I don't have it off the hand. Sorry. Did I see a hand, Bjarne? I saw a hand over here. Oh, Scott. Uh-oh.
Presumably you're not thrilled with forward list, but my question really is, do you have some suggestions on the kinds of data structures you'd like to see added to the standard library?
So the comment is, I probably am also not thrilled with forward list. I'm not. Although I'll point out forward list does have half the overhead, which is at least a nice benefit if that's the right data structure. But the further question was, what data structures would I like to see added to the standard library? Number one, unequivocally, is an excellent open addressed hash table. That is the single most important data structure for like day in, day out programming to improve performance. I mean, by such a huge margin that it's kind of terrifying. And what I'd really like to see is I'd like to see its name be easier to type than all of the bad ones. Because I don't know, like I can get up here and I can give these talks, and you guys are a great audience, and I hope you go and tell everyone else you know about this. But this is a really poor way to ensure that programmers actually use the right data structure. I actually have a much higher faith in their unwillingness to type more characters, leading them to the right data structure. Which, I mean, I don't mean that to reflect poorly on you all. I am a very lazy typist, okay? So that's actually, I don't know how much further I would go from that. The other things that I kind of want to see, there's some fabulous work around building a sorted map interface on top of a vector that gives you very good efficiency guarantees and actually represent kind of the modal operation of stop acting like a map and let me add data to it. Now make it act like a map again, right? Sort it once, batching up the sorts. Those type of data structures would be really, really useful for mapping and for other things, I think. I'd also like to see a very easy way to have something like forward list, for example. A great forward list implementation I saw, it uses tagged pointers to represent whether the pointer needs to be deallocated. Now this seems like a trivial thing, but the way they would use this is that they would batch large allocations and then chain together contiguous nodes in it, using a tag to indicate that that node didn't need to have its memory released. And they always deallocated from the tail up, and this allows you to do really kind of nice pooled allocations even outside of the data structure. And I would love to see that. I would love to see pooled allocations inside of the existing data structures. I think that would be great. I really want to find a solution to the kind of allocator problem that does not exist in the type system and does not involve dynamic dispatch. Because right now we have either the current allocators, which invade your type system and cause all kinds of API guck, which I don't like, okay. But on the other hand, we have a really, really great attempt by Pablo and Alistair and other people to solve that with polymorphic allocators that aren't in the type system. But they introduce dynamic dispatch and indirection around the memory allocation. And that's kind of yuck too. And I don't have a solution to this. I don't know what the solution looks like, but I really want one. Like I really, 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 really want one. I don't know that there are that many more data structures to add if we have good control of allocation. Other questions? I mean, I'll keep talking. You guys, unless you guys want me to get off the stage, you should stop asking questions. All right, well, thank you very much. Oh, no, one more. No, one more. A noble attempt.
The whole time I've been feeling bad for the guy at the start who said that passing a pointer and you said no. And it's like maybe not passing a pointer, but passing a reference to reuse the memory.
So I'm gonna let you know a secret. When you pass references, you're passing a pointer. I know that it would be nice if it weren't, but it is.
But I mean, reusing the memory in the vector, it's like while it's get line, you know, it's a common.
No. Just please. Just return it by value. Like, I'll let you in on another crazy thing. If you return it by value, and the compiler can ever inline that function, the compiler will actually like deduplicate your allocations for you. It's fine. The compiler can see allocations. This is why I don't want a dynamic dispatch around them. As long as the compiler can see the allocations, it can actually fix a lot of these things, and you can keep the clean code. Yes. No, actually, I think GCC does a pretty good job of this too.
So are you saying that like the result of reserve n would only be done once?
Yeah. Oh, don't even. Yeah, I mean, it's just map, okay? I pick on map not because map is worse or better, but because it's used orders of magnitude more often. Yes?
What about persistent data structures? Does that call for linked lists?
What about persistent data structures? Does that not call for linked lists? Well, define persistent data structures.
They are immutable to everybody, and you just make copies of the structure itself, but not updated.
Okay, so the idea is immutable data structures, which are not being updated. Yes, immutable data structures are perfect for linked lists, and they tend to have higher cache locality properties because you tend to not mutate them. You tend to have decently hot reads on them. They're not being updated very often. They're still slower than cache, like densely cache populated data structures, but sometimes algorithmically they're the only option available. right? And this is where the algorithm data structure tie kicks in most often, are things like immutable data structures, where you have algorithmic constraints like I have to have sorted data. It doesn't matter whether I want sorted data or it's slow to produce it, I have to have it, because if I don't have sorted data, the rest of my algorithms fall over and there's no hope, right? Sometimes you can do that, but sometimes you can't. If you have to have sorted data continuously during updates, right, there are very few options left to you, and it's an algorithmic constraint that introduces itself. The weird thing is that that's insanely rare, right? So rare that I have yet to see a single piece of code that actually needed that. Every piece of code that did that, you can go in and say like, well, you don't really need to keep it sorted all the time. There's this nice batch point where we could sort, right? But I'm holding out the theoretical possibility that it exists. Maybe. Yes?
Like a lot of the current compromise for persistent data structures is that they're actually using pretty fat nodes, like a hash array match trace, for instance.
So the comment is that for a lot of the persistent data structures, they're trying to use larger nodes in order to compensate for this. I mean, that's the fundamental argument behind B-trees, is that rather than doing a binary tree, we'll stuff a whole bunch of things in a single node so that we get some cache locality. And most B-trees tend to pick cache-sized nodes, roughly, where they can, or nice multiples of cache sizes to maximize this property. And yes, that's great. And it's a fabulous way to engineer cache locality into an algorithmically constrained problem space. But it's also incredibly rare. Like, if you're working on a file system, absolutely. But you're also probably not using standard map if you're working on a file system. Yeah. All right, any other questions? Otherwise, I think we should get some food. Oh, one more question.
So what do you think about page arrays? Because, I mean,
Say that again.
what do you think about page arrays? So arrays where you have not complete contiguous block of memory, but pages. I mean, they're little over here.
So the question is, what do you think about paged arrays? Paged arrays are just B-trees, just any other chunked linked data structure, right? It's where you're essentially trying to amortize the cost of the links by putting more things into each linked node, right? And it is an engineering trade-off, but it's complex. It tends to have more bugs. It tends to be slightly slower. It may be the only option, but I would avoid it if I could. The question is, where is the point that you want to do a binary search versus actually doing a linear search because it's short? My suggestion is that you call the binary search function and you file a bug against your standard library implementation until it makes that determination for you correctly every single time. Yes, standard library implementer.
In the case of lower bound and friends, we are unfortunately required to perform login. I don't believe we can invoke n.
So Stefan points out that the standard requires that you invoke login, and so that's not an option. And I challenge that.
If it's order login, then we could be sneaky.
Because if it's order login, then the constant factor is fine, and I'm pretty sure we could make this work. Any other questions? And maybe we could actually get to dinner.
Why does the standard library tends to just provide one flavor of each data structure? Like there's only one list or maybe two lists now, only two maps instead of providing several different flavors?
So the question is, why does the standard library only provide a single flavor of data structure rather than providing a large number where people can pick and choose? I have a lot of answers to this. I will give the short ones. The first one is, do you trust developers to pick and choose? I don't. And I don't mean that as an insulting thing. I just don't think that they have the time, energy, or should spend the time or energy trying to choose between 50 different, like, crazy tree implementations. I would much rather that there are reasonable defaults. The second reason is that as you tend to have more variations, I think you tend to be domain specialized. And when you're domain specialized, you probably just don't want anything from the standard library, or at most you want some utilities from the standard library to build your own data structure. And so I think you see very rapid diminishing returns there, where it would actually be better to just make it easy for them to define a domain-specific data structure that does exactly what they want. That actually tends to have really good results in practice. And with that, I think we should get some dinner. It's been a pleasure. Thank you very much.